This demonstration illustrates how to use the graphical user interface processing SHEMAT and how to navigate in it. In working with the SHEMAT software, it is best for you to store your work always on a flash storage, carried along with you in the exercise sessions. After inserting it into the computer, create a new folder named, for instance, SHEMAT. In this folder, you need to place separate folders for each of the exercises named after the exercise. Then, from the desktop, open the folder Programme im E.ON ERC, or in English, Programs in E.ON ERC, and there the folder Simulation. In this folder, you will find the icon for Processing SHEMAT. Click on it, and the program will start. After a welcome page, the graphical user interface for SHEMAT will open. In its top row, you see a series of drop-down menus which you will need to work your way through from left to right. Make sure to address all points in these drop-down menus, except for those which are grayed out and appear somewhat transparent. Start by opening the File drop-down menu. Click New Model, create a new folder named 1 on your flash storage, and there a subfolder named 1A. Now you need to change the File Manager default path from C Program Files SHEMAT to this new folder. Start by selecting your flash storage device. In our example, it is F. Identify your folder 1A on F and name your new model 1A. The extension .ps for processing SHEMAT is added automatically. After this is done, you are brought back to the main page of the graphical user interface and may proceed to the next task. Proceed now to the grid menu for defining the numerical mesh for the domain defined in model 1A. Click Mesh Size and choose how you wish to input your data. You may select either horizontal XY layers or vertical XZ or YZ cross-sections. For model 1A, select vertical. Now you need to input the numbers of columns and rows. Calculate them from the given horizontal and vertical model dimensions of 7,000 meters and 3,600 meters, respectively, and from the given cell sizes of 50 meters in X and Z. If calculating correctly, you will come up with 7,000 divided by 50 equals 140 columns, and 3,600 divided by 50 equals 72 rows. The grid editor displays the mesh. In this editor, you can zoom in and out, rotate and translate the grid, and switch on or off duplication of parameter values assigned to grid nodes. Additional menu items in the top bar of the editor will be explained later as they become relevant. Exit the editor by clicking the exit icon. And confirm that you wish to exit by clicking on Ja or Yes in the selection box. Proceed now to define the cross-section thickness. From the grid menu, select cross-section options. The default value is 1 meter. Since problem 1A requires a cell size of 50 meters times 50 meters times 50 meters, set the horizontal thickness of the cross-section to 50 meters. And confirm this setting. This will take you back to the grid main menu. From there, now select Property Zones. An editor will open displaying the grid. Here it will show your cross-section. In 3D models, you can use the arrow up and down buttons to navigate through the horizontal or vertical cross-sections of your 3D grid. In this editor, you can define separate zones of your model with different property values. Using the Value menu option, you may assign values either to individual nodes using the Array option, assign one single value to all grid nodes using the Reset Array option, or define monitoring points. Alternatively, you can use the editor to define property zones, either by cell input, the fourth icon from the left, or by zonal input, the fifth icon from the left. Switch between duplication on or off, second icon from the right, as you need while using the left, right, up or down arrays to move the cursor for marking grid points you wish to assign to this property zone. As Model 1a requires only one property zone, confirm the default value, leave the property zone editor, and confirm saving of any changes made. Now proceed to the Type main menu, in which you make your selections regarding the type of simulation to be performed, the type of coupling to be invoked between the different partial differential equations for flow, transport and reactions, and for the amount of real-time information you wish to receive as the simulation is performed. There, select Settings. A window pops up for choosing settings regarding the simulation of groundwater flow, heat transport, species transport and chemical reactions. For Model 1a, select Heat Transport and confirm the default suggestions. As a result of your selection, the other processes are grayed out and you do not need to specify settings for them. Confirming your selection takes you back to the Type main menu. There, select Coupling. A window pops up for choosing settings regarding various options for coupling groundwater flow, heat transport, species transport and chemical reactions. You may keep water properties constant, the default being that they are updated with respect to temperature and pressure. Make rock properties, thermal conductivity, specific heat capacity and density vary with temperature. Vary porosity according to chemical dissolution or precipitation. And update permeability with regard to porosity. For Model 1a, just confirm the default suggestions. This takes you back again to the Type main menu. There you select Info Results. A window pops up regarding the amount of runtime echoes you wish to receive from the program and file formats for runtime information and graphical output. At first, always select Full Runtime Information. This helps identifying errors in your input file. Only rarely you will succeed in writing an error-free input file right away. Select VTK file and TechPlot. Confirming takes you back again to the main menu, where you proceed now to the Time menu. There, accept the default suggestions regarding stress periods and nonlinear iteration and proceed to Solver parameters. There, select BiCG-STAB, the biconjugate gradient stabilized method. A window pops up regarding time weighting between fully implicit and fully explicit, the preconditioner to be used, the convergence criteria and the maximum number of iterations allowed. Confirming the default suggestions takes you back to the Time main menu. There, proceed to Monitoring and confirm the default settings, as Model 1a does not require setting monitoring points. This takes you back again to the main menu, where you proceed now to the Heat menu. There, proceed to Initial Temperature field, after which the grid editor opens, the cursor being placed in the top left corner of the grid. After right-clicking on this cell, a box opens for adjusting the cell value from its default value, which is 10 degrees centigrade. Set it to 11 degrees centigrade, as required by Model 1a, and confirm your selection. Then switch the duplication mode on. And move the cursor all the way to the right along the top boundary. Then switch the duplication mode off and leave the grid editor by clicking the leftmost icon. Finish by confirming that you wish all changes to be saved by clicking Ja or Yes. At this point, let me explain some of the options of the grid editor in more detail. First, open the Value drop-down menu and click on Array. This displays the cell values as entries in a numerical array, which can be modified by you. Clicking on Reset Array allows you to initialize the entire array with one value. For cell-by-cell input, press the plus icon for switching to the value entry mode, if it is not displayed already as pressed. Information on each cell is obtained by holding down the Shift, arrow up, key of your keyboard and pressing the left mouse button. This opens the cell information dialog box. Holding down the Control, Steuerung key of your keyboard and pressing down the left mouse button opens the Search and Modify Cell Values dialog box. It allows you to modify either individual cell values or values of cells which fall into a specified range. You may zoom into your grid by drawing a rectangle with a pressed left mouse button. This is particularly helpful for inspecting and modifying cell values in large grids. Zooming out displays the entire grid again. You may choose between two modes of input: the cell-by-cell mode or the zonal mode. In zonal mode, you assign one value to all cells within a polygonal zone. Click on the required number of cells for defining this polygon. Close it by clicking on the first cell again. Then right-click inside the polygon to open the Zone Value dialog box. Input the desired value and leave by confirming. Then you are free to return to the cell-by-cell input mode, to switch on the duplication mode, and copy values in the cell-by-cell input mode. Now return to the main heat menu for completing the other entries. Start by clicking Boundary Conditions, after which the grid editor opens, the cursor being placed in the top left corner of the grid. Now you need to assign code numbers to the boundaries for identifying the type of the desired boundary condition. The default setting for all grid points is 1, meaning no flow. For the top boundary, set this value to -1, meaning temp, as model 1A requires a constant temperature at its top boundary. Now switch on the duplication mode and move the cursor all the way to the right along the top boundary. Now, temperature of all nodes at the top boundary will be held constant at the initial temperature during the entire simulation. Next, proceed to the switch for activating and deactivating the duplication mode and switch it off again. Then move the cursor to the lower left corner of the grid, right-click on this cell and set its value to 2, meaning WSD, as model 1A requires a constant specific heat flow across its bottom boundary. As before, switch on the duplication mode, move the cursor all the way to the right along the bottom boundary and switch the duplication mode off. Then click on the leftmost icon to leave the grid editor and confirm that you wish all changes to be saved by Ja or Yes. Now return to the main heat menu for completing the other entries and click on Thermal Rock Properties. This opens a box showing all thermal rock properties and their default settings for a default number of 15 property zones. For model 1A, adjust the property values for one property zone only where required and select the method of weighting of fluid and matrix contributions to bulk thermal conductivity. Then leave by confirming your selections. This returns you to the main heat menu again, where you click on Fluid Heat Production. As this is not required in model 1A, accept the 0 default setting, which takes you back again to the main heat menu, where you click on Constant Heat Flow. This opens the grid editor for you to identify nodes of constant specific heat flow in the same way as you marked nodes of constant temperature before. Model 1A requires a constant specific heat flow of 80 milliwatts per square meter at its bottom boundary. Therefore, move the cursor to the lower left corner of the grid, right-click on this cell and set its value to 0.08 watts per square meter. Now, as before, switch on the duplication mode, move the cursor all the way to the right along the bottom boundary and switch the duplication mode off again. Then click on the leftmost icon to leave the grid editor and confirm that you wish all changes to be saved by Ja or Yes. This takes you back again to the main menu, where you proceed now to the Models menu, where you click on Create SHEMAT Input File. If your operating system uses commas instead of points as decimal separators, as, for instance, the German language version of Windows does, a warning alerts you to change this. To this end, go to Start, open Systemsteuerung or Control Panel, click on Region und Sprache or Region and Language, and change from Deutsch, Deutschland, to English, USA. Accept this change now by clicking on Übernehmen or Accept, and leave this menu by clicking on OK. Now click again on Create SHEMAT Input File. If your input file is found complete, you are now asked whether you want to start a SHEMAT simulation right away. Confirm by clicking on Ja or Yes. SHEMAT now starts the simulation and displays the requested runtime information in the DOS console. If everything worked out all right, you will see as the last message, Run OK. For viewing your results, now proceed to the Tools menu, where you click on Result Viewer and select Spatial Distribution. A selection box pops up in which you need to specify what is to be displayed and how. Select a 2D projection in the XZ plane of the temperature field. Now start the plotting routine by pressing Apply. As a result of Model 1A, you should now see this colored cross-section.